So yeah, I'm here to talk about Mithril, like the full node client on Solana. And let me see. Yeah, so who are we? So Overclock is a blockchain validator team. It was started in Solana in 2022, and we expanded to run on a few more chains. But we're primarily Solana focused, and our primary model is to contribute open source improvements and tools to support the chains that we validate. So I'd like to spend a little bit of time talking about the importance of full nodes. The reason is that, like, the reason why full nodes are important is because it's the only way to get trustless access to a blockchain. So by trustless access, I mean that a full node is the baseline of what it means to be trustless. There is a little bit of a misconception that ZK proofs and fraud proofs give you trustless access to blockchains, but this is not true because any kind of proof system, fraud proof or validity proof, it adds an additional layer of trust. And that's basically like the security assumption. So if you use like BLS 12381 or anything else, you often see things like there's 128 bits of security. So these are all additional layers of trust that you're adding over what is normally there for a full node. And obviously, attestations is basically saying that 60% of the stake has signed off saying that this is the state root. So that is also not trustless. It's actually a weaker trust assumption than even like GK proofs and fraud proofs because with attestations, you're trusting the supermajority. An easy way to explain this is the probability of 67% of the stake lying to you is not the same as the probability of like 128 bits of security, right? So that's actually the reason that's actually the reason full nodes are important. And the last point is actually quite interesting because it touches on a very subjective definition of decentralization, which is something that we'll go into in the next slide. So if you see this has been discussed a lot on Twitter and a lot of other places as well. Like the core of decentralization is a user's ability to run a verification node. So the cost, like one measure of decentralization is the cost it takes to actually verify the chain. So as you know, like running Solana on like data center grade hardware is actually quite expensive. You require very big machines and you require gigabit bandwidth. And it's also technically challenging. Like it's not like you can just download a binary or build it from source and just run it. So yeah, there's a second tweet as well, which is, whether what's the value of this argument in the first place? Like if it's too expensive to run a node, then you cannot know the rules of the node. Because if you're trusting a network to run the consensus for you, and if you're trusting them, then they can change the rules of the chain without you knowing. So running a full node basically enables you to verify the rules on your own, right? And so there's a bigger question here, like why has a verifying full node on Solana not been built? So like you can see a tweet by Anatoly saying that it's just that nobody has tried to minimize the requirements. This is kind of like a trade-off line where validators are trying to use more powerful hardware, like more state-of-the-art machines and everything, and try to reduce latency as much as possible to execute blocks as quickly as possible. Whereas for full nodes, the argument is for decentralization, you want to keep the cost low. So that's, it's like they're counter arguments to each other. So again, David Hoffman, who I disagree with a lot on a lot of things, is actually right about this. So he talks about minimizing the resource cost to verify a chain, right? And so this is the reason we started building Mithril, like a verifying full node client, and it's written in Golang. It was originally started on Feb 2024. So it's like an easier to follow implementation of the core state transition function. So what do I mean by state transition function? Like every blockchain can be looked at as a state transition function. The state is like the entire accounts DB. You take a block, you play the block, and the state changes. So, and the state transition function encodes all the rules for like applying the block. This is consensus. This is signature verification, gas checks, transaction validity, even block validity. Like if you say that a block cannot occupy more than 48 million units of compute or whatever it is increased to, like all these rules have to be verified, right? So that's the state transition function. So Mithril's job is very simple. It's an implementation of the state transition function, meaning if you feed a block to Mithril, it'll execute it and move the state forward. Nothing else. So that's why we emphasize that Mithril is a full node client and it's not a light client, meaning that all the blocks are executed in full. The exact rules of the state transition function, whatever is designed for the Solana protocol, they're all executed. So yeah, and Mithril is not a validator. Like validators do a lot more things other than full nodes. They produce blocks, they vote on consensus, they get staked. So Mithril's goal is not to do that. Mithril's goal is to connect to the blockchain, just play blocks one after the other, right? So yeah, this is something that Toli has been mentioning since 2022 and even earlier, honestly, that the most of the computational overhead for a validator comes from the fact that it's trying to aggressively stay at the tip of the chain and also like playing the consensus protocol. So one of the things Mithril does is that if you already can filter out confirmed blocks, you can still verify the confirmations by counting like 67% of the stake voted or not, but you don't need to do the exact consensus algorithm. Like, I mean, it's being changed to Alpenglow, the new consensus protocol, but TowerBFT is a good example of how much more is done. Like Solana validators first play the block, then they maintain a stack of all the votes and they maintain a tree in order to figure out whether, like it's, speculatively they execute ahead of verifying consensus. So Mithril doesn't need to do that, which is one of the biggest, it reduces, like if you're trying to execute multiple blocks and you don't know whether they're confirmed or not, you have to maintain multiple pieces of state and memory. So by playing already confirmed blocks, Mithril actually reduces the resource overhead by a good amount. And validators usually over provision because they need to handle like massive ingress of transactions. Like they need to verify all of these transactions and they need to produce blocks. They need to schedule all these transactions into blocks. Like none of this is actually done for Mithril. So yeah, just going through like a general principles that we try to follow. Like because Mithril doesn't need to aggressively stay at the tip of the chain. Like for validators, the difference between 300 milliseconds and 200 milliseconds is a lot because it can mean a massive difference in revenue. You can miss like an MEV bundle. Like, so validators are incentivized to aggressively stay at the tip. But for Mithril, it's actually okay to relax it to even like 800 milliseconds behind the tip. It's not like a huge big deal. Like you don't miss your block production slot because, well, Mithril doesn't produce blocks, right? So we're making some trade-offs where we're like, it's fine to not be that aggressively at the tip, but you can focus more on throughput, meaning you're going to play multiple blocks at once, which leads us to the second point, amortization. So an easy way to explain amortization is that if you're doing like, if you're playing a block, then verify signature, execute, load from database, store to database. And if you're repeating this for each block, you're performing varied tasks for each block. So this is something that Aragon on Ethereum has also done, which is if you have 100 blocks, instead of playing them sequentially, first verify signatures for all the transactions and all the blocks that you have. When you do this, you kind of gain like a performance benefit. Like modern computers are, like modern hardware in general is very good at amortization. Meaning if you keep verifying signatures one after the other, you don't need to load the programs. The CPU L1, L2 caches are also like reused. So you tend to gain like more performance benefits with amortization. Simplicity is the next important thing. So as I said, Mithril is purely an implementation of the state transition function. You won't find anything in the code base that doesn't involve like verifying a block and playing the block. Like there's no extraneous concepts, right? So, and separation of concerns. So we build Mithril to be very modular, where the state transition function stands on its own and is separate from the networking section. So the benefit of that is that when you separate things, you can optimize them individually without, impacting other components of the software. So yeah, I just want to go over a couple of the milestones that we already finished and ones that we will be doing. One of our earliest milestones when we built Mithril was we needed to build an implementation of the SVM. So the SVM is a core part of the state transition function. It's like the Solana virtual machine. It's what plays the transactions. So yeah, the very first part was like, okay, take the Solana SVM, take the BPF SVM, BPF VM, which is a part of the SVM, and re-implement that in Go. And we were able to make use of Firedancer's conformance test suite to ensure that, it was compliant and it's not breaking. And yeah, we finished this in September 2024. And yeah, the next part is verifying mainnet beta itself. Because one thing you need to know is that when we say SVM, we don't mean just the virtual machine. There are a lot of programs in Solana that exist outside the virtual machine as well. Like these are like the system program, the vote program. All of these also need to be implemented. So by milestone 2, we had a complete implementation of the state transition function, and we're able to feed it blocks and play the blocks. Like we didn't really optimize anything with the accounts DB or anything till then. And we first full epoch was replayed in May 2025, couple of months back. And yeah, so the final milestone, now we are able to actually get a snapshot, unpack the snapshot to populate the state. And we're also able to stay at the tip of mainnet beta, which means that when you run a Mithril node, it's going to keep up. So here are some benchmarks from one of our previous runs. So if you notice, like this is a very small machine. Our memory usage is between 6 to 8 GB. This is significantly lower than like most other hardware. And even the CPU utilization is very low. And we're able to actually keep up with the tip. And this kind of validates what Anatoly and a lot of people have been saying from the beginning, right? Like if you optimize your code to just implement the core Solana protocol, the hardware requirements are really not that high. There really isn't anything that complicated. It's mostly reading from disk, like executing a block and storing the state back to the disk. Everything else is just like you can optimize around that. So that's actually the reason our memory usage is also quite low. Because if your entire account state is stored on disk and you have a decent enough SSD, then you don't even need to aggressively cache in memory. So yeah, the future path, obviously we want Mithril to be able to run under very low constraints. We accomplished like having it run on low hardware, but the next goal is to also reduce bandwidth requirements when fetching blocks. There's a few other bugs that we want to eliminate that we're currently working on. Some performance improvements, like we actually don't even need to play the transactions in parallel because it's such low compute actually. So, and yeah, we'll be adding more functionality. And by the end of the year, before breakpoint, we plan to have like a audited release. And yeah, just as a thank you, the Solana Foundation supported us, Solomon and Jonathan, and the initial version of the BPF virtual machine that we took into Mithril was actually written by Richard Patel from Firedancer. And obviously the Firedancer team helped us a lot with testing. And obviously like the Solana Labs and the Anza team and, all the people who stake Overclock and have helped us make this possible. Thank you.